We'll go back to doing things the way we're supposed to do them in Calc 2 now, but I'm going to go there by using these inappropriate formulations that we've had previously. Firstly, the mass. What if the mass density, rho of x and y, were a constant number, just rho? Then in the inside integral, the antiderivative would just be rho times y. You would have to evaluate that at f of x and g of x and subtract to get, since the mass density is a constant, I can factor it out of the remaining integral, and I find out that the mass is the constant mass density multiplied by the area of the region, just as it should be in the case where the mass density is a constant. In the case of constant mass density, this last expression tells me the mass of the region. In a similar way, if I want to calculate the moment about the y-axis, I have to calculate this integral, and in this case, rho is an actual constant, and inside the inner integral, we treat the x as though it were a constant. The antiderivative is going to be x times rho times y. I have to evaluate that at y equal g of x and y equal f of x, and subtract. In the case of constant mass density, the moment about the y-axis is the mass density times integral from a to b of x, and the remaining factors are what compose area between the two curves. We obtained this formula just before we went off and looked at the inappropriate language, so our more complicated and sophisticated ideas reduce down to what we should get in the case where the mass density is a constant. Before we took our side trip, we never did calculate what to do about the moment about the x-axis, but now, with our more sophisticated idea, we'll directly see what the answer ought to be. Again, rho is the constant mass density. This time inside the inner integral, I have a factor of y. The inside antiderivative is 1/2 times constant rho times y squared, and I have to evaluate that between y equal g of x and y equal f of x. This time the result looks very strange. It's the integral from a to b of 1/2 times the constant mass density times the square of f of x minus the square of g of x with respect to x, but I can make this look more like the other ones if I remember that quantity a squared minus b squared is a plus b times a minus b. Those a's and b's are just generic formula, not the limits of integration. Inside the integral, I have the difference of squares. I can think of that as being f of x plus g of x multiplied by f of x minus g of x. If I factor it up in that way, I can write the moment about the x-axis as we said. The rho is an actual constant. I can pull it out of the integral. I could pull the 1/2 out, but I'm not going to. I'm going to group the 1/2 with the factor of f of x plus g of x. By doing this, I can make the last part of the integral look the way the others looked, f of x minus g of x dx, mass density out front, and f of x plus g of x over 2 represents the typical y-coordinate. This makes good sense in the case of mass density being constant, because then it's a reasonable supposition that the best representative y-coordinate for a vertical strip would be in the middle, the average of f of x and g of x. So to summarize, our constant mass density problem has been completely resolved now. If you look in your textbooks, you'll see that these are the formulas that your textbook supplies for a vertically simple region of the type we've been looking at. We obtained these formulas by thinking in a more sophisticated way and then dropping back to the simple case. I hope that this is understandable. I may have gone a little overboard on the center of mass stuff, but at any rate, I hope everyone has a good day. I'll talk to you again soon.